In our final section of Chapter 7, we are going to combine a lot of ideas of the first two sections and look at mean and median, two common application problems of the probability density function and cumulative distribution functions. So first, let's review what we learned in 7.1 and 7.2. Given that small p of x is a density function, then we know that the probability that someone in a population has a value of the characteristic from x equals a to x equals b is going to be the integral from a to b p of x dx. In the first two sections of this chapter, we talked a lot about how this integral is related to the percentage of the population that has a certain age, or it could be thought of as the probability. So looking at this as the specific example, the probability that someone is between the ages of 20 and 30 years old is going to be 20 to 30 p of x dx, and this is where this p of x is specifically the density function for ages in whatever population we're talking about. Similarly, we talked about the cumulative distribution function, that's capital P of t, and that's associated with little p of x. In fact, we know that the derivative of the cumulative distribution function is itself the density function. And usually we think about that in the reverse order. So we know that p is also the antiderivative of little p. And since we're talking about integrals, we're talking about antiderivatives, and this is where that capital P is going to show up. So if we're talking about the cumulative distribution function, we know that the probability that someone in a population has a value of a characteristic less than some value t, then we can write that as the integral from negative infinity to t of p of x dx, and that is by definition capital P of t. That's by definition the antiderivative of the function. So if you look at an example, the probability that someone is less than 30 years old is going to be the integral from negative infinity to 30 p of x dx. And we're going to commonly think about in a specific example, for instance, this one, if we're thinking about age, we can't have negative age, so our lower bound is going to change into a 0 there, as that's the smallest age we can have. So the probability that someone is less than 30, we're just going to count all the people from 0 to 30. Or we can just write this as capital P of 30. So again, this is a review of section 7.1, 7.2. If this seems fairly new or you want to go over that again, please rewatch those videos or do some more practice problems with those concepts. But now let's move on and talk about mean and median. So we're talking about distributions of people, where populations have more or less of them. So for instance, we talked about in ages in a college dorm, most people are going to be about the same age, in 18 to 21 years old or something like that. And how the distribution is laid out is very important. And one important concept of that is a measure of center. Where is the center of that distribution? And there's two common measures of center, that being median and mean. So we're going to review these concepts in a very simple finite form, and then we'll talk about it in terms of the distributions we're going to be thinking of. So when we say the median of a bunch of numbers, so here we have 2, 2, 3, 4, 6, 9, and 20. The median is just going to be the middle number. Nothing more than that. So since there are 7 numbers, we're looking at the 4th number in that sequence. It doesn't matter how big or small the other numbers are. It just matters which one is the middle one. So again, we note that even if this 200 or this 20 were a 200, that would not change the median at all. It's still the middle number. The mean is another way of looking at the center. We also think of mean as the average number. And to find that, we can just take the average of those numbers. So that is adding all of those numbers together. And then dividing by how many numbers you have. We said there are 7 numbers, so we will divide by 7. If we do this calculation, we're going to get about 6.57. So here again, we had the median, a measure of center. We found the middle number was 4. And here we found the mean, the average number, was about 6.57. Two numbers that give us an idea of the center, though they mean different things. And in some cases, the median is better to look at. Some cases, the mean is better to look at. We're not going to talk about all of that in this class, but very quickly, if there is an outlier in the data, it's usually better to use the median as opposed to the mean, because we talked about the example of if this were a 200 instead, the middle number wouldn't change, but the mean would change a whole lot. And that kind of affects which one we should use, the median or mean. So now let's talk about mean and median in terms of a distribution. We're going to talk about a lot of numbers. In fact, we may be thinking about an infinite amount of numbers. So a median of a quantity X distributed through a population is a value capital T, such that half of the population has value of X less than or equal to T. So again, this is our idea of the middle number. T is going to be our median. And that means that half the population will be above T and half will be below T. Right, so we have our little group of numbers. Here's T right in the middle. We're saying half the population is going to be above and half of the population is going to be below. And maybe we include T, maybe we don't include T. Since we're going to be talking about a lot of numbers, it's not going to make a big difference whether we include it or not. So that's what we're saying. T is going to be our median value. Half the values lie above, half lie below. So if P of X is our density function, we can say that the integral from negative infinity to capital T, again, our capital T is our median, of P of X dx should be equal to 0.5. That is the percentage of things that are less than T should be equal to 50%. So this integral is the percentage of things in our population less than T, or the percentage of things from negative infinity to T. And we talked about that. Another way to say this is capital P of T, or the cumulative distribution function, where we plug in T. And it's equal to 0.5, 0.5 from being 1/2, 50%, half the things lying below. So when we talk about finding the median of a distribution, we are going to plug in the density function into this equation, and we are going to solve for T. So let's look at an example of some distributions. We're going to recognize distributions as graphs, capital or lowercase p of x. We're just going to sketch where is the median. Note that what we're talking about here are x values on the x-axis, and that's what the median is going to be, is different x values. Maybe we should make a quick note of that. That medians here, median is an x value, or a t value if that's our variable that we're using. So we're looking for a median in this first example. We're looking for some x value that's going to represent the middle of our distribution. In this first graph, the middle is just going to be the very middle x value. In this case, it would be exactly 2.5, as that's the middle of 0 and 5. Now, that's not always going to be the case, but for this one, we know it's the case because the area on the left is equal to the area on the right, which means that 2.5 is right in the middle. So this is half of the area, and this is also half of the area. Since this is a simple function to look at, and it's very easy to calculate the median. Note that here, lowercase p of x is exactly the function 0.2. So if you wanted to find the median, you would plug into your function the integral from 0 to t, 0.2 dx equals 0.5, or 1/2. And you would solve that equation. 0.2x evaluated from 0 to t is equal to 0.5. 0.2t minus 0.2 times 0 is equal to 0.5. 0.2t is equal to 0.5. T is going to be equal to 2.5. That's what we mean by solving that equation. And we'll do some more example problems like that in the next video. So the next one we're going to look at is this straight line. This time it's not going to be just a constant function, but it has some slope. It gets bigger as we go to the right. That means that more stuff is going to be near 25 here than is going to be near 0. So the median should be closer to that right-hand side. And again, what we're saying is that the area on the right is going to be about the area on the left. This is a bit of a guesstimate here, but that's what we're looking for. It should be further to the right than we had in the previous problem. The third one, now the lines are curvy, but it's the same idea. Maybe the median would be closer to the left-hand side because of the bigger hump. Half the area is on the left, and half the area is on the right. And for the last one, this is our bell curve that we've looked at a few times already. And here the median will be exactly in the middle because this is a symmetric function. We know that half the area on the left and the right will be the same. So the top of that hump is going to represent the median. So now let's look at the mean and know that we're going to do some more practice problems in the next video with median. So let's look at our problem we want to do. We want to find the mean age of people living in the US currently. So one way that we could do that is we take the sum of the ages of all people in the US and divide by the total number of people in the US. And that may be a doable thing, but it would take a very long time to do as there are just so many people. So we're going to use an integral to help us with this calculation. And note that would take a lot of calculations to do all the adding and then the division of the total number of people. But that's what we're going to base our idea of mean off of. So instead of finding the actual thing, we're going to estimate the sum of all ages using some integral. So first we're going to consider the number of people and the sum of ages in a small age range, delta t. That is the range t to t plus delta t. We kind of see that right here, t to t plus delta t. And this is going to be the idea that if we say t is equal to 20 years old, maybe delta t is 1 day. So we're saying that this is going to be all the people who have their birthday today that are exactly 20 years old. And we can make delta t as small as we want. So when we're trying to find this, we want to find the number of people with the ages between t and t plus delta t. That is going to be the percentage of people in the population with that age, and then multiply that by the population. If we say that again, we're saying that P of t times delta t is the area of that rectangle, and that is going to be the percentage of the population with ages between t and t plus delta t. That is the integral from t to t plus delta t, p of x dx, or p of t dt. So if we take that percentage of the population and we multiply it by the population, this will give us the number of people with that age. With age t. Then the more important question is, how do I deal with the sum of ages of people with that age range? And by the age range, we're really just thinking of people with almost the exact same age that are all 20 years old. So if I know the number of people with that age and I add up all their ages, I'm just going to be adding up the same age over and over and over again. And the number of times I'm going to do that is the number of people with that age, which I found above. And that will give us, in this case, 20 times the P of t delta t times the population, what I found up here. But of course, I'm not going to be thinking about 20. I'm going to be doing age just t itself. So that's where we get our formula, t times P of t delta t times the population. And when we look at the formula for mean on the next page, we're going to see where does this extra t come from? And that's this idea that we're adding the same age over and over and over again, t times. Or sorry, the number of people with that age times. So putting this all together, that was the sum of ages of people with a specific age. If we look at the sum of all people, the sum of ages of all people, then we are going to add over every age. We're going to let t range over all ages. And I can factor out the population out of all of those terms. And when we have a sum like this is an infinite sum, we're going to be adding all over all ages, we can rewrite that as an integral by letting the difference in the age range, the delta t, go to 0. We could look at all the people with ages exactly 20, but exact maybe be within a minute or a second or even smaller than that. Which means that we do have that the sum of ages of all people is going to be equal to the integral over 0 to 100. We're saying that all ages are going to be within 0 and 100, t of P of t dt times the population. The extra t, we show where that came from on the previous page. If we then divide by the population on both sides of that equation, we get that the mean age, which is the sum of ages of all people divided by the population, is just going to be equal to that integral, 0 to 100, t P of t dt. Again, the most important thing to remember in this equation is there is an extra t in that equation. So now let's look at mean here in the definition. If a quantity x has a density function p of x, then the mean value of the quantity is going to be equal to the integral from negative infinity to infinity. We're looking at all values of x times p of x dx. It's going to be the integral over everything times an extra x on the inside. We'll do some practice problems with mean in the next video so we see how to work with that equation and find the mean in a distribution. Last thing we're going to do here, though, is we're going to look at some distributions and think about where is going to be the mean in those distributions. We talked about the median. Let's just write the median down for all of these. There's a new one on the left. That one, the median might be here, a middle value. The area on the left is equal to the area on the right. The mean, so this is all median here. The mean is going to be the same for the first one. It's the middle value. There's nothing weird going on. It might be a little bit bigger, or it's going to be about the same for the second one as well. And it's going to be the same for this normal distribution. Because of the symmetry of what we're dealing with, there's no differences in the measures of center. However, in this third one, the mean is going to be a lot further to the right than the median. And this is because there are outliers way out here, which are going to skew the mean in that direction. So although it's not the focus of this class, we do know that if the mean is greater than the median, then we know that there are going to be some outliers, or the data is skewed to the right. There's going to be bigger things in our outliers. Whereas the other way around, we have the outliers to the left. So again, in the next video, we're going to look at the calculations of how to find mean and median, and that will conclude our topics of probability.